Hey everyone, it's Mr. Canfield. After filming the first Riemann Sums video, I realized that we need a follow-up to kind of go over some actual problems beyond just how a Riemann sum works and how we find one. So I'm going to go through and do the word problems. This is normally where we see Riemann sums. Every now and then we'll see just a straight up do a Riemann sum that has this many subintervals and blah blah blah. So anyway, here we go. It says, I'm on page 179. A traffic light turns red and the driver stops the car in 5 seconds. So it looks like here's the graph of that. There's a table, and I'll read these numbers as I go through since they're kind of hard to see. Over those 5 seconds, the speeds in feet per second are recorded. The graph to the right plots those points with straight lines joining them. Find the area under this quote-unquote curve using a trapezoidal rule with 5 trapezoids. Interpret the answer and explain why this is an approximation. Okay, I can explain why this is an approximation at the very beginning. The thing is, these 6 times that we check the speed is constantly changing. It's getting lower and lower and lower and lower and lower till we hit a speed of 0. And so because of that, the exact area that we're going to be calculating right now is going to be of these kind of rigid shapes instead of the smooth curve. So, all right, I'm going to remind you that we're going to make trapezoids, and we're going to make 5 of them. Remember that this trapezoid right here is a trapezoid where the sideways is actually the height, and then these are our 2 different bases. So if I want to find the area of this one trapezoid, remember that it's 1/2 times the 2 bases added together. What's this base and this base? So it's going to be 2 different y values, right? So the y value at 0 is 88, and the y value at 1 is 60. And you might remember that instead of having to find them each individually like this, what I'm going to be able to do is essentially add this one once. This one is going to happen for this trapezoid, and then it's also going to happen for the next trapezoid. So I can add the 60 twice, and I can add this one twice, and this one twice, and this one twice, and then this one once. So in reality, oh wait, well, this is 1/2 base times height, and the height for this is the distance there. And if I look on the table, it says 0, 1, 2, 3, 4, 5. So the height is always going to be 1 for these. So instead of doing a single trapezoid, I could say, let me do the area of all the trapezoids. Say it's 1/2, 88 plus twice 60 plus twice, my next one says 40, plus twice, my next one says 25, and then 10 is my next one, and my last one is 0, and we only add that one once. So then I can add all these up and get something, and cool, my calculator's not dead, so I'm allowed to be lazy. Let's see, 88 plus 120 plus 80 plus 50 plus 20. Oh, I forgot the times the height at the end. So I got 358, and then divided by 2, I got 179. So I got my area is 179. So what does this approximate? So let's see, the area under a curve. I don't think I told you guys this in the last video. This area is actually representative of the integral of this curve, or this shape that we have. So the integral would be the thing that I took the derivative of to get this. And so this is the accumulated, if this was velocity, well, what did I take the derivative of to get velocity? Position. So 179 is actually the position, the accumulated position, the amount of distance it traveled over those 5 seconds. So let's see, if I'm dealing with feet per second, then this is going to be my position. My displacement is going to be 179 feet. So we're going to look at a few more examples of this, and hopefully that'll kind of help make sense out of this. So you jump out of a plane. Hopefully you have a parachute. Okay, before your parachute opens, you are in free fall. While your speed increases, your acceleration decreases as you fall because of air resistance. So this is like a real thing. This is a more realistic example. Every time we've done these before, we've kind of pretended air resistance is not a thing. And then Mr. C gets mad at us next door. But now we're actually taking air resistance into account. So the table on the right gives acceleration a in meters per second squared for the first 6 seconds. If time is measured on the x-axis and a is measured on the y-axis, find the area under this so-called curve using a trapezoidal rule with 6 trapezoids and a midpoint Riemann sum with 3 rectangles, and interpret the area using correct units. So I'll do the 6 trapezoids first. It's very similar to our last one, right? I don't even need to draw it necessarily if I understand, the distance in our x values is going to be, or our t values in this case, is going to be like the height. So 0 to 1, 1 to 2, 2 to 3. Our height is going to be 1 every single time. So our area is going to be 1/2. The bases all add together times 1, our height. So let's see our bases. So if you remember in our previous one, trapezoid, the way that it worked was the first base only got counted once, and then all the in-between ones get counted twice, and the last one only gets counted once. So because of that, I'm able to say here, if I'm using 6 trapezoids, I have I have these 7 values. Here's my first trapezoid, here's my second, here's my third, here's my fourth, here's my fifth, here's my sixth. Let's see, 9.81 plus 2 times 8.03 plus 2 times 6.53 plus 2 times 5.38 plus 2 times 4.41 plus 2 times 3.61 plus just that last one once, 2.78. So if I do this, and I actually don't believe that it's being lazy to use your calculator for this, because if I use my head for this, and my head makes a silly mistake, it's very, very hard to catch. 5.38 plus 2 times 4.41 plus 2 times 3.61 plus 2.78. All right. So I'm a little concerned. I'm afraid I made a typo, and it's very hard for me to check right now. I'm just going to assume that I'm correct, and then you can yell at me if I'm wrong. But I got 34.255. So my area was equal to 34.255. Now, remember, area is going to be a representation of the integral. And so the integral of acceleration, what did I take the derivative of to get acceleration? I took the derivative of velocity. So this is actually velocity. And this is my accumulation of velocity. So let's see, this is my acceleration, right? So this is essentially going to be my like how much velocity we picked up in that time. So if I was going to do the midpoint sum for this using 3 rectangles, well, so now I need to figure out what my 3 rectangles are going to be. So I want to go from 0 to 6 and break it up into 3 equal pieces. Well, that's going to be rectangle, rectangle, rectangle. And remember that for midpoint, we used the middle y value between the 2 sides of the rectangle. So in this case, we're going to use the y value at 1, the y value at 3, and the y value at 5. So let's see, area is equal to, well, I know it's length times width, or base times height, and it turns out the base in these is from 0 to 2, from 2 to 4, from 4 to 6. Our bases are 2 each time, so we'd say 2, and then add our 3 different heights together. 2 times 8.03 plus 5.38 plus 3.61. So let's see what we get here. 2 times 8.03 plus 5.38 plus 3.61 I got 34.04. So, oh, I should have made, since these are velocities, I should have said feet per second. Not feet per second, oh, meters per second, sorry. Meters per second. So, very, very close to each other. Much smaller calculation to make here. And since we don't have the actual function given to us, I can't find the true integral and the true answer for either of these, 4 or 5. So let's see what our next one says. When intervals are not the same, instead of doing this kind of everything together approach, we're going to have to do a broken apart approach. I've seen these on the AP exam time and time again, and if you remember that, like if we realize what it's asking, it's super easy. Over a period of an hour, vehicles are lining up to go over a bridge. The table to the right, why are they lining up to go over, whatever. All right. The table to the right shows the rate that vehicles join the line. Use the trapezoid rule. Sometimes they'll say trapezoidal, that's why I said that funny. Use the trapezoid rule to approximate the number of cars that have lined up in that hour. And so we're just going to take this trapezoid, whatever the heck it looks like, and then this trapezoid, whatever the heck it looks like, this trapezoid, whatever the heck it looks like. Have I made my point yet? I'm just going to take those 1, 2, 3, 4, 5 trapezoids and add them up. So our first trapezoid is going to be 1/2 base 1 plus base 2, so that's 20 plus 25. Notice how I'm adding the y values together there. And then what's our base? 0 to 10. Or sorry, our height, sorry. From 0 to 10, our height is 10. So there's our first one. Plus our next one, 1/2. Our bases are 25 and 45. And our height is 10 to 25. Oh, it's off screen. Canfield. Our height is 10 to 25. That means from 10 to 25. That's 15. Plus, you get the point. Maybe you don't. I'll just keep going. Plus, our next one. We add our two heights together again, our two y values. Man, I'm mixing my words up really bad. I'm trying to go quickly. So, anyway, remember that base is our y values on these. It's kind of silly. It's kind of backwards. So our base is going to be from 45 to 50. So 45 plus 50. And then the height is 25 to 40. It's another 15. Oh, but look at this next one. It's only going from 40 to 45. So that one's only going to have a height of 5. And then 50 and 20. So you might be of the persuasion that it's better to actually get 45 there, 70, and just like just less writing. I think that's really good. I'm just trying to show where everything's coming from. And our last trapezoid, let's see, 1, 2, 3, 4. Yep, our last trapezoid, our height is going to be 45 to 60, so 15. And then 20 plus 50. So if you want to write this in a much simpler way, you could say 1/2, and then instead of putting the 1/2 every single time, and say, okay, then I've got 45 times 10 plus, what is this one? 60, 70, 70 times 15, and then 95 times 15, and then 70 times 5, and then 35 times 15. Might save you some writing. But anyway, let's see what we get. So we're going to figure out exactly, well, not exactly, we're going to figure out an approximation for how many cars have lined up over the course of that hour. Let's see, 45 times 10 is 450. 70 times 15 can't be bothered. 95 times 15 can't be bothered. 70 times 5 is 350. 35 times 15 can't be bothered. All right, I have the 0.5. So I got 1,900 cars line up that hour. So this is an interesting thing that we can do. We can know how fast something's happening and kind of backward map it and figure out exactly how much we accumulate. Oh, I know it's snowing this many inches per hour. Oh, I could figure out how many inches total we acquired. Now, this is not perfect. This is an approximation, and the perfect one of this comes from the integral of things. So if we had a function to go with this, we could then use an integral. All right. Let's look at our next one. A swimming pool containing 63 gallons of water. 63,000 gallons of water is too cold, so the pool drains water while pumping in warmer water. The table below shows the rate that water is pumped in and the rate the pool drains in gallons per minute at various times over a 12-hour period. Using the Trapezoid Rule, how many gallons of water are in the pool at the end of the 12-hour period? This is an AP style question right here. So what we need to figure out is how much water, let's see, it starts with 63,000 gallons. It gets more water pumped in, but it also loses water. So what we're going to want to do is we're going to want to take that 63,000, we're going to add new water, and we're going to take out the pump out water. So basically, I'm going to use the trapezoid rule. I'm going to do a trapezoid rule for the water pumped in, and I'm going to do a trapezoid rule for the water pumped out, and then just do the basic math beyond that and use more common sense beyond that. So let's do water pumped in. Let's see. So I've got 1, 2, 3, 4, 5 trapezoids I'm going to have to do. So I'll pull the 1/2 out front. And let's see, my first trapezoid has a 300 and 200. So 300 plus 200 is 500. Times my height of 0 to 2 is 2. Plus, my next one is 200 to 300. That's another 500. And this time my height is from 2 to 5, so it's 3. Then 300 and 400, that's 700. This one is 5 to 8, so it's also 3. 4 and 2, so that's 600. And then 8 and 10 is 2. Barely had enough room here. 10 to 12 is another 2, and that's it for 300. So if I calculate this out, this should be the total amount of water that's pumped in. Let's see, 500 times 2 is 1,000. 500 times 3 is 1,500. 700 times 3 is 2,100. 600 times 2 is 1,200. And then another 600. So for me, this is the fastest way that my brain is going to go through and do it. I'm going to write like some intermediate stuff, do some more work from here to here, just to save myself some typing. So we get 3,200 pumped in. So we started out with 63,000 gallons. We pumped in 3,200 more. Let's go and find out how much is getting pumped out. And again, these are approximations. Since I don't have an exact equation, this is the best I got. So let's see, 1/2. And here's the cool thing. The 2, 3, 3, 2, 2, that's the same. Because it's the same from 0 to 2, 2 to 5, 5 to 8. It's just these numbers are going to be different. So we get 300, 300, which is 600 when we add them. And then 3 and 2 is 500, so that's 500 times 3. Then let's see, 200, 200 is 400. And that's another 3. 200 to 150 is 350. Oh, it looks like we're pumping out less water than we're pumping in. See, 350 times 2, and then 150 and 100 is 250. So I'm going to do the work here. I'm going to get 0.5 times, parentheses, so 1,200 plus 1,500 plus 1,200 plus 750 plus 500, 2575. So I got out, it was 2575. So how many gallons of water are left in the end? Well, we started with 63,000. We gained 3,200, and we lost 2,575, leaving a grand total of, so I just did the reverse, but I gained 625 gallons over that. So 63,625 gallons. So let's review what the thinking was that went into this. So it says to use the trapezoidal rule. These bases are all different, so I have to do a bunch of separate trapezoids. And then the issue was, it shows the rate that the water is being pumped in and the rate the pool drains. So we're draining and pumping in new water. So we're losing the pump out, or I guess it's just draining. Whatever, I wrote pump out. It's the same idea. We're losing this. So whatever number we got there, we wanted to subtract it. The pumping in was being added, so that's why we added. So So I think that's a good examination of word problems that we can see for these. So I hope this was helpful. Fine. Okay, I'll do the last one. I'm like, I just want to finish the video and upload it. But I'll do the last one. Let's see. At 5 p.m., a subway train leaves a station with 20 people still on the platform. Oh, those poor 20 people. Having just missed the train. Womp womp. Let P of t represent the number of people on the platform at time t waiting for the next train, which will arrive at 5:05 p.m. Values of P of t are shown for every minute in the chart. Okay. A. Examine the graph below. Find a left Riemann sum and describe the units in which it is measured. So, I'm a little confused where we have these two different graphs here. Oh, okay. Actually, no, I don't know what's going on. Oh, I think he's showing like a sideways Riemann sum. We don't normally do sideways Riemann sums. I think he's just having us think outside the box a little bit. So, anyway, he's given us this to do a left-hand Riemann sum, and I like that he's already drawn it for us because it saves me some writing. But notice how out of these rectangles, they come from here, and he only picks the left-hand y value out of these 5 rectangles. And our width of each of these rectangles is 1, so it's going to be 1 times those 5 different y values. So, or p values, I guess, here. So our area is going to be 1 times 20 plus 50 plus 80 plus 100 plus 140. 1, 2, 3, 4, 5. Notice we don't add the last one for a left-hand sum. And if we were doing a right-hand sum, we would start here and go down, and 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 here and go down. And because of that, a right-hand sum, we would not actually use that first y value. So left-hand sum leaves out the last one, right-hand sum leaves out the first one. So if I go through and do this, 20 plus 50 plus 80 plus 100 plus 140, we get a total of 390. So let's see. Examine the graph file left Riemann sum and describe the units in which it is measured. Okay. So let's see. P of t represents the number of people on the platform. So yeah, this represents a strange a strange thing. We can take the integral of this. We started with people, though. What's the integral of people? And so if we think about the successive derivatives that we would take of this, like if we were to take the derivative or the slope of this, we could say, oh, this is the average number of people per minute that are coming in. And then if the original is our just people that we have, well, then what did we take the derivative of to get people? And so you'll notice that the derivative was people per minute. If we took the derivative of that, it'd be people per minute squared. The derivative of that would be people per minute cubed. So if we kind of reverse that, and if the plain one is just people, we took the derivative of people minutes, or people times minutes. 390 people minutes. This makes very little sense to me, but this figure represents the approximate total number of minutes people waited for the train. So I just read that. I had to go look this up. I actually struggle with the reverse derivative of just like the plain number. But yeah, this would be called people minutes. Kind of silly. But yeah, this has something to do with the amount of time people are waiting for this train. So yeah, anyway, hope going through and doing the actual, sums was helpful for you. Now doing the homework should be a little bit more straightforward. So yeah, have a good one. Bye.